So I'm very happy to be in Paris this week, and I should thank the organizers of the whole program. It was a very nice week. So I'll talk about spatial coupling. So Henri introduced spatial coupling in his tutorial, right? Yes? Okay. Sorry?
So I said, see, just to describe, Rudy and these guys introduced it to the world.
Yeah, but in the tutorial this week, you introduced spatial coupling. But, okay, so Henri explained that spatial coupling is a useful engineering construction for constructing error-correcting codes that achieve capacity. So this was, the first construction was given by Feldstrom and Zigangirov. And then, after a few years, people understood these codes. If you set up the boundary conditions correctly, they perform very well. And finally, Tom Richardson and Rudiger Urbanke and Srinivas Kudekar proved that these codes achieve capacity on any channel. So from this point of view, that's a very nice engineering construction. So in this talk, I would like to advocate another point of view where we use spatial coupling not as an engineering construction to achieve a good performance of something, but as a proof technique to investigate phase diagrams of maybe inference problems or constraint satisfaction problems, or maybe codes. But we don't want to deduce properties of the spatially coupled system. We want to deduce properties of the original uncoupled system. So it's a bit like when you want to prove a theorem in real analysis, but maybe you have to go in the complex plane. Okay, you come back in the real plane. Okay, so, yeah, so maybe before I continue, I should say that the set of ideas that I will present, in fact, maybe it's a set of ideas that have spanned the last 10 years, and I've collaborated with various people here, and so there are many contributions in what I'm going to say. Okay, so that's what I was saying. To use spatial coupling as a proof technique, now I have to choose a problem, and so I can choose the problem of Ldpc codes, and this is what I will do. Or I could have chosen the problem of KSAT, proving bounds on the thresholds of the KSAT problem. But okay, I had a set of slides on this KSAT. I thought I would prepare a new set of slides this week. So, even if Henri tried to convince me not, but I did so. So what I want to show is a proof of the so-called replica symmetric formula for non-coupled Ldpc codes. So the replica symmetric formula that I'm going to prove, in fact, it's a formula that allows you to compute exactly the conditional Shannon entropy for an Ldpc code when you use it for communication over a general channel. So I won't limit myself to the BEC. I'll take essentially any binary input, memoryless, symmetric, output symmetric channel. And so I have this Ldpc code here with the check nodes that constrain the bits of your code. I'll consider only regular Ldpc codes, so fixed degrees, right degree and left degree. And so given the output of the channel, that it's a received message, I call here y1 to yn, that's this vector y, that I represent in terms of the likelihoods or the half log likelihoods of the received symbols. So that's the log of the ratio of the two transition probabilities, whether you have sent a 1 and you receive a yi, or you sent a -1 and you received a yi. So Q is the transition probability of the channel. Epsilon here will be the noise parameter. So think of the BSC channel, binary symmetric channel. So think of epsilon equals 0 is zero noise, epsilon equal half is maximal noise, or think of the BEC if you wish. So epsilon goes from 0 to 1, but you could take any other channel. And so when you do map decoding, what you have to study is an inference problem. In fact, you have to, given y, reconstruct the input word. Okay? I work in the ±1 language. So what is this probability distribution here? I have a product over all checks of the code that go from 1 to m, so all these squares. And each check constrains a certain number of bits that are attached to the check. And the constraint in the ±1 language is that the product of the bits are equal to 1. So that's the indicator function that says that the check is satisfied. You make this product. And then because you observe the output of the channel, you have a bias, a prior on your code bits that you want to reconstruct, given by hi, the likelihood, the log likelihood associated to the channel. Okay, and my problem is that I want to compute exactly, I want a formula for the input-output entropy, Shannon entropy, associated to this probability distribution. So the h of the vector x given the vector y. And I would like also to study phase transition for this problem. There are phase transitions as you vary the channel parameter epsilon. Okay. So there are two types of phase transitions in such problems. One that I call static. From the point of view of statistical physics, this is a thermodynamic phase transition. You might call it an optimal ensemble phase transition from the point of view of coding. So this phase transition is the following. There is a threshold that I'll call epsilon map for map decoding, which is the smallest noise value beyond which this conditional Shannon entropy averaged over the Ldpc ensemble, that's the expectation is the average over the Ldpc ensemble, normalized by the block length, the smallest such epsilon such that this uncertainty here is positive, strictly positive, so that you cannot decode anymore. So below epsilon map, this thing here is 0, and okay, it doesn't quite imply maybe that the probability of error is 0, but basically one can show that you can decode as long as this is 0. Okay, so this is what I call a static thermodynamic phase transition. I think of it as a non-analyticity of this function as a function of epsilon. Because before epsilon map, this function here in the infinite block length limit is rigorously 0 by definition, and then it becomes positive. So this is a non-analytic function. One can show it's a continuous function, okay, but it's flat and then it goes up. So epsilon map is a the function is not, okay, maybe even in fact the first derivative in this case jumps, okay, but at least you know it's not analytic. So this is what I call thermodynamic or optimal phase transition. Then you have a second type of phase transition I call dynamic or algorithmic. In coding here, the algorithm that we will use is a message passing belief propagation decoder. And this phase transition is not really associated to this object. You do not see it in this object. Okay? This dynamic phase transition is in the region where this object is rigorously 0, so you see really nothing. Okay? So this dynamic or algorithmic phase transition is the largest noise epsilon such that the belief propagation algorithm or decoder can recover the input word. Okay? And of course, since well, this is a suboptimal decoder, you must have that epsilon BP is less or equal to epsilon map. You have this information, but we don't have much more. And to avoid any confusion, so I fix my Ldpc code ensemble. I take, for this talk, regular ensemble with fixed degrees for variable nodes and check nodes. This ensemble, as such, does not attain the capacity. The capacity is given by some noise threshold, Shannon's noise threshold. So epsilon map is strictly less than Shannon. It should be a strict inequality here. Sometimes it may happen that these two coincide, but generally the inequality here is also strict. So think of strict inequalities here. So one basic question is, can we compute these thresholds? Can we even compute this function completely? So, you know, for physicists, the answer is yes, we can compute, and they did so. I guess physicists contributed to the computation of this map threshold, and belief propagation threshold was, I guess, first computed by in encoding theory anyway. But now the question that comes is, can you also compute, especially the map threshold, rigorously? Okay, you have some predictions by physics, statistical physics theories. Can you make these predictions rigorous? So I just want first to give a high-level view of the main theorem that I will attempt to prove. I won't really prove it, but I'll give the main ideas. So I give an informal statement. It will become much more technical later. Okay, so this is something we obtained with Andrei Giurgiu and Rudiger maybe 2 years ago. So what we can show is the following, that for binary input and symmetric channels and regular, we limit ourselves to regular codes because, okay, we stopped working at some point. It becomes more and more technical. Okay. What is important is maybe not that the code is regular, but that we need for this theorem to have large degrees, left and right degrees. So we fix the rate to 1/2, say, but the degrees have to be large enough, but finite. Okay, finite. It's not an asymptotic result. They are finite. Then there is a technical nuisance that the degree of check nodes, the right degree, has to be even. I'll say why later. But okay, forget about this technicality. You can compute this function, and the result is given by the supremum over a space of probability densities that are defined on the real line. So this is what you might say a one-letter characterization for this conditional entropy. So you have to compute the supremum of some kind of functional. It's a functional of probability densities that sit on the real line. Okay? This functional is what in statistical physics is called the replica symmetric functional, or maybe sometimes, well, it's related to the Bethe and the cavity free energies. Let me not go in that direction. I'll write it down later on. So for those who know the theory of Ldpc codes, you don't have to know exactly what's this functional. The only thing that's important is to know that when you attempt to compute the supremum, you have to write down the stationarity condition. So you write the condition that the derivative of the functional with respect to this probability density, so functional derivative, equals 0. And what you find is the density evolution fixed point equation that I wrote here in some funny kind of notation that captures the equation for general channels. But since we had the tutorial of Henri and I guess Rudiger also spoke of the BEC channel. In the case of a binary erasure channel with erasure probability epsilon, this equation I'm writing down there is a scalar equation. So X becomes, this probability density becomes, in fact, can be described by a scalar variable. Let's write it like this. That is, in fact, in 0, 1. It's the erasure probability that you have in the density evolution for the BEC. And the equation is simply a scalar equation, x equal epsilon 1 minus 1 minus x to the power r minus 1 up to the power l minus 1. So when you see an x to the power r minus 1 in this talk, there will be lots of them, just think of it as this function of a real variable where x is the erasure probability. And when you see something like y with this symbol, that's a usual convolution, in fact, to the power l minus 1, just think of this as a real variable y to the power l minus 1. Okay, so we won't need much more. And C epsilon here is the channel density. So in fact, it's the probability distribution in the language of these likelihood variables. Okay? So y has a certain probability distribution given your input code word, and you do a transformation of variables, it induces some probability distribution for these likelihood variables. That's my C epsilon, so it depends on the channel noise. Okay, so I want to illustrate how to use spatial coupling as a proof technique to prove this kind of formula. And this is valid for uncoupled Ldpc codes. Of course, it's also valid for coupled Ldpc codes, then this functional is more complicated. But I'm not interested in coupled Ldpc codes. I just use them to prove something about the uncoupled formula, ensemble. Okay, so before I go, I have to introduce a few tools. And in fact, since the result has nothing to do with spatial coupling, in fact, spatial coupling will come at around the 10th slide, I'm sorry. So I hope I get there. So I need to introduce a few tools. So how do you compute first the belief propagation threshold, this algorithmic phase transition? Well, belief propagation allows you to estimate what I call the marginal in quote unquotes, because it's not the true marginal, but it's a belief propagation marginal estimate of the marginal of bit xi given the observations, and that's an iterative algorithm, so this depends on the number of iterations t that you use. And because the variable is binary, you can describe this probability distribution by just its log likelihood parameter that I call HIT. And this is computed by taking what comes out of the channel, so kind of prior, you know about the bit, and then you add these improvements that to the log likelihood that are computed by these message passing belief propagation equations. Okay, so here you have messages that go from variable nodes to check nodes, and then you have messages that go from check nodes, the hat, to variable nodes. So if you have never seen these equations, it doesn't matter, it's just an iterative algorithm. And now to compute the algorithmic threshold, you have to track this algorithm. So how do you track the algorithm? Well, this is tracked by this famous density evolution formalism, density evolution equation. So what is density evolution here? Well, you take these messages that flow from variable to check nodes at time t, assuming all messages are independent in this algorithm. So you say that they are distributed according to some density x at time t, so that's a probability density, and that's the random variable if you wish. And it turns out this probability density satisfies this iterative equation, so it evolves with time. Probability density at time t minus 1 allows you to compute the probability density at time t, so it's not very mysterious. In fact, you see here you have the channel distribution is convolved with something. So because you have a sum here of this random variable with the rest, so this leads to a convolution. Here you have a sum of L minus 1 messages that enter in your variable node, so you have a convolution to the power L minus 1. And these hatted fields here, or likelihoods, they are computed from the other ones through this complicated product of tan and so on. So that's not quite computable with a usual convolution, but there is another operation that we call the box convolution that captures this at the level of probability densities. It's a kind of convolution because if you would take the log of the product, you would have a sum. So think of this as a kind of convolution. And now you initialize density evolution with zero knowledge. So you say that you don't know your bits when you start decoding. So that's a delta Dirac function, a Dirac mass at the likelihood 0. So if you take these likelihoods to be 0, you only know hi. So this is what that's why that's the good initialization. And what you want is to drive this density through this equation to the Dirac mass at h equal infinity. Because if this h is infinite, then you know that with probability 1, this bit is +1. That's maybe your input code bit. So you want to drive these densities to the Dirac mass at infinity, at infinite likelihood. And if this happens, this is driven to this, then you can decode. So the belief propagation threshold, how is it computed? Well, it's the largest noise value for which, starting with this initialization, you're driven to the fixed point x infinity equal to the Dirac mass at infinity. Okay, so above some threshold, you will get stuck to some non-trivial distribution, and you cannot decode anymore. Okay. So there is a nice way to visualize this BP algorithmic transition in terms of the belief propagation generalized exit curve, it's called. So Rudiger introduced a map exit curve for the BEC. I want to work on general channels. That was a bit the challenge of the work, to extend everything to general channels. There is a map generalized exit curve that I will use, and there is a belief propagation generalized exit curve. So, okay, that's a complicated formula, but what it says is the following thing. By definition, this g-exit curve here is the partial derivative with respect to the channel noise of some quantity. What is this quantity? In the H, you have a density, and the density here is simply the density of the likelihood of the decoded bits. Okay, so it's the density of this variable, and you take h of this density is the entropy, just the Shannon entropy of that density, if you wish, or said maybe more correctly, h here, this functional here, maybe you don't recognize exactly Shannon's entropy, but it's in fact the entropy of this marginal BP distribution of xi given y, written in the domain of this hi. So it's a linear functional in terms of the density of this variable, and this will play an important role. So you take this entropy, this Shannon entropy for this marginal, the BP marginal, you take the partial derivative with respect to the channel noise only. Now the channel noise comes in the fixed point of density evolution also, but you don't differentiate with respect to that epsilon that's hidden in here. You differentiate only with respect to that, so at least formally you might want to write it like this to get confused. Okay, so if you plug in the Dirac mass at infinity here, so H is concentrated at infinity, exponential minus infinity is 0, log of 1 is 0, so you find this entropy is 0. So this implies then that the BP exit curve is flat, it's 0 up to the belief propagation threshold. Okay, so you have this GBP of epsilon as a function of epsilon, that's 0 up to epsilon BP, and then maybe it jumps, maybe it doesn't jump. I don't care for the moment. Typically, it will jump, and it does something, and one can also show it's monotonous with noise. Yes?
Just wanted to make sure that
yes.
The x that you have here and this density evolution, which is really a parameter evolution, so is that x, which is the probability mass assigned at infinity, and you want to make sure that it, as you iterate, they converge to 1?
So yeah, if you wish, so for the BC, this erasure probability is the probability. So okay, the notation is you want it to converge to 0, in fact. So you have x, that's the probability that you have mass at h equals 0. So that's what I call delta naught, plus 1 minus x, the probability times the mass at infinity.
Okay, so x is the converse of x, 1 minus x.
Yeah, somehow, yeah. When you go to the BC, in the literature, the convention is such that so delta infinity corresponds to x equals 0. So it's the probability that a bit is erased that you have not decoded it.
So the critical epsilon is the largest epsilon such that this curve stays below the diagonal, that and there's the unique fixed point.
Yeah, yes. On these curves, when you study this fixed point equation, it's the critical epsilon for which this side stays below the diagonal, as you say. Exactly. Okay. Now, I want to describe the static phase transition, and then I'll start comparing the two. So that is the statistical physics prediction for the conditional entropy averaged over the code ensemble. And this is given by the supremum of the so-called replica symmetric functional, supremum over some set of what we call symmetric densities, but these are densities over R. And this functional has an explicit expression, and I wrote it here. You don't have to read it very carefully. But again, you have the entropy of the same, basically, almost the same that I had before when I defined the BP exit curve, except that here you have the fixed point of density evolution, and here you have a general density. And then the only thing that's important in the rest for today is that all this does not depend explicitly on the channel noise. The channel only comes in the first term. Okay? If you write the stationarity condition for this functional, then you find, okay, you say that the functional derivative is 0, you find the density evolution equation. Okay, so in fact, this functional here, I also wanted to say, is nothing else than this potential function that Henri introduced in the literature and in his tutorial, okay? Except that it's a potential functional in a functional space, so it's a rather complicated object. So here, think of this as a section through this functional space, and don't read what is on the axis. Just think that, so what is on this axis, think of it as an axis in the space of densities, or think of it as this variable x, this real variable x. On the vertical axis is the value of this potential, and these curves are parameterized by the channel noise epsilon. Okay? So the statistical physics prediction is the following. Now, here you have the point where this little x is driven to 0, so your density is driven to delta infinity. Okay? So as long as you're below the BP threshold, HBP is my epsilon BP now. So as long as you're below the BP threshold, if you start here and you start iterating density evolution, you will be driven by gradient descent, basically up to the point where you can decode. Okay? At the BP threshold, there is a second minimum that develops, and density evolution gets stuck at this local minimum. Okay? And then you cannot decode. Now, in fact, this is not the absolute minimum, so you're still below the map threshold. Because if you could overcome this barrier, maybe you could decode. What happens is that at some critical epsilon, in fact, this gap between the point where you have the mass at infinity and this minimum vanishes. And when this gap delta E vanishes, that's exactly the point where you are at epsilon map. Okay? But you have to prove this. Okay? So what we do is that we define a potential threshold, and the potential threshold, by definition, is the biggest epsilon such that the local minimum here is equal to this other minimum here. Okay? So it's the biggest epsilon such that the gap vanishes here. And the prediction by statistical mechanics that we would like to prove is that this potential threshold, defined like that, is equal to the map threshold. Okay. A useful tool to make these proofs is to introduce another exit curve that is a map generalized exit curve. And that's exactly the exit curve that Rudiger had yesterday if you take the BC channel. But in general, you want any channel, and you define it so that it satisfies the area theorem he was talking about. And so now the area theorem becomes trivial because you just put it in the definition. So the good definition is just the following. You take the Shannon conditional entropy, you take the derivative with respect to channel noise, normalize by the block length, you take the lim sup, or if you know that the limit exists, in fact, we can prove the limit exists. So that's the definition. And by definition of epsilon map, this will be strictly equal to 0 below epsilon map, because this is 0 below epsilon map. And above epsilon map, it will jump to something. So above epsilon map, maybe epsilon map is here. So here it's 0, and maybe it jumps to something like that. So maybe this is G map of epsilon. Okay, and this definition is tailored so that the area below this curve is equal to the rate because of the code. Because if you integrate this derivative, you can easily show that you get the rate of the code. Okay, so recall where we are. I introduced two types of exit curves. The belief propagation exit curve, which is the partial derivative with respect to channel noise of the entropy of the BP marginal. That's the BP marginal, computed by BP. And the other one is, well, the definition is that. But, you know, because we know the result we want to prove, statistical physics suggests that this is given by the sup of some functional. At least formally, you expect that this map curve is equal to the derivative of the stat-phys replica symmetric formula. Okay? And now if you mess around here, you can convince yourself, so I'll show this, you can convince yourself that most probably these two curves, I don't have color, but these two curves here basically are equal above the map threshold. So in this region, the G map of epsilon equals the GBP of epsilon. Okay, you take the definitions, you take the prediction of statistical physics, and in this region, the two curves should be equal. So the way to see this is to say, okay, this supremum will be attained, say, at a special density that depends, x star, that depends on the channel parameter. So I put x star here, and then I have a derivative which is partial with respect to the explicit epsilon that enters in the channel density. And if you compute this from the expression of HRS, you find something that's almost like the BP exit curve, except maybe this x star, the supremum, x star is where the supremum is, say, attained, is maybe not exactly the same as the density evolution fixed point. And then you have to differentiate with respect to the internal dependence of the soup with epsilon, okay? So you write some kind of functional derivative, but you know, you don't have to really write it. You know that, in fact, the derivative of HRS with respect to x at the supremum should be 0. It's because I said this yields that's the stationarity equation, I mean, for the soup. So whatever this is, this should be 0 if you can control these functional derivatives. So finally, the map should be equal to the BP if the soup here is attained at the same x infinity than density evolution. And from experience on the BEC and so on, we know that this can happen only above the map threshold. So all this suggests that these two curves should be equal. And this is what we are going to try to prove, because if you know that these two curves are equal, then by integrating this relation, we can get the end result. Okay? But this is more easily said than done. So, okay, now let me state, I have the definition of these exit curves, and let me state the theorem that we proved a bit more formally. So, for symmetric channels, high enough Ldpc degrees and even check node degree, the map threshold is equal to the potential threshold that I defined before, where this potential has the two minima exactly at the same level. Above the map threshold, the two curves are equal. I suggested this might be true. And finally, we prove this replica symmetric formula. So why do I state the theorem this way? Because for at least two reasons. In fact, for almost 10 years, I think, finally we knew that here this is an inequality that goes in that direction. This was known from methods I'll say a word about in the next slides. We also knew that there was an inequality in this direction, okay? And we also knew that there was an inequality in this direction. And in fact, these three inequalities were all the same inequality. And it was frustrating for 10 years not being able to prove the converse bounds, okay? So this is where spatial coupling enters, to prove the converse bounds. These inequalities that we knew, there were various ways to prove them. One way is by the so-called interpolation method. Maybe I'll say a word. I don't think I'll have much time. Another way is for people in statistical mechanics, maybe, I don't know, in the audience, but it was by correlation inequalities. The third way was by degradation techniques that are in the book of Tom and Rudiger. Okay, but in fact, these two statements turn out to be simply a consequence of the first statement. So, you know, this problem is quite constrained, in fact. It turns out that if I know how to prove that epsilon map is equal to epsilon potential, where the epsilon potential is this threshold where you have this potential functional that is parameterized by the channel noise, so this HRS of epsilon as a function of x. The potential threshold is the epsilon potential where the two minima are at the same height. If you know how to prove the first statement, then the curves are completely constrained, and you know they are equal above the map threshold. You also know the third statement. Okay, so in fact, with spatial coupling combined with some interpolation methods, we prove, in fact, the first statement. That's the technical contribution, and then you have to work a lot because to prove the rest, but it's basically you just have to work. So I'm not sure how much time, 10 minutes? Okay, so let's see. I wanted to show, that 2 implies 3 and that 1 implies 2. And then I wanted to talk about 1, but I'll go directly and talk about 1, okay? So believe me that 1 implies 2 and 2 implies 3, okay, fine. So I skipped 2 slides here. So as I said, I just want to prove that these 2 thresholds are equal. So the potential threshold equals the map threshold, and that is a prediction of the replica method at the end. Okay, so what we knew for years, and this has a long history, is that this Shannon conditional entropy averaged over the Ldpc ensemble is certainly greater or equal than the soup of this replica symmetric potential functional. And this implies immediately that the map is less than the potential, because this can be, this is flat until the map, and if you're below the potential threshold, this soup is 0, I think. Yeah, let's not talk about signs here.
No, I mean,
yeah,
it
depends.
The opposite way, because you define potential as a function of u, not a function of
right.
h.
Right. Stated like here, it's correct, right?
Yeah.
Okay. Okay. So, so this was known, and that's a long story to prove this kind of inequality. It started with Guerra in Antoninelli for the spin glass models on dense graphs, but then Silvio Franz and Leone extended this to the SAT problem or sparse graph systems, Pachenko also, and then Andrea Montanari, and we also did something specifically for coding. There is another version of the interpolation method that I'll talk about a bit later due to David here, but to prove something slightly different. Okay, so spatial coupling, I come to spatial coupling now, is useful to prove this inequality, the converse inequality, which by itself has nothing to do with spatial coupling, okay? My system is just not coupled. So how are we going to do that? I just show the big steps of the main steps of the strategy. So we take the base ensemble, the Ldpc base ensemble, and we construct a spatially coupled ensemble, okay? So I won't describe in detail this, but that is a code. Each code here has a length n. You have n code bits. For the spatially coupled structure, you sort of couple various random graphs here, and you multiply the length of the code by L, or 2L maybe. This is still an Ldpc code, a much bigger Ldpc code. So it has a belief propagation threshold. And this belief propagation threshold will depend on the length of the chain and on a parameter W that is your coupling width. So for example, for W equals 2, you couple two neighboring codes here. Okay? You also have to adjust the boundary conditions so that the bits are well constrained at the boundary so that they are known, say they are known. So then you have this decoding wave phenomenon. Because you know the bits at the boundary, you can, with belief propagation, decode all the bits in the whole chain by running belief propagation, starting with the known bits at the boundary. And this you can formalize it and show that the belief propagation threshold for the chain of length L coupled over a width W will tend to the potential threshold. So basically the best you can do, because this will be the map a bit later, it tends to the potential threshold as the chain length goes to infinity first and the coupling width goes to infinity later on. Okay? So this kind of result was first proved, say, by Srinivas, Tom, and Rudiger, not in terms of the potential threshold, what they call the area threshold that I didn't introduce in this talk. And with Henri and his students, and Henri did it for the scalar BEC type systems before, we proved this without the notion of area theorem, but just with the notion of potential threshold. So this is called the threshold saturation phenomenon. Okay, so you improve your belief propagation threshold up to some ultimate point. That's the potential threshold. Okay, so let me not, so I just recall this potential threshold is when this potential functional has a gap delta E here that closes. So the two minima are at the same height. And this is supposed to depict a decoding wave that is decoded. And proving this theorem means analyzing some kind of density evolution equation for the coupled system. So it's a bit long to show how you do this, but maybe Henri gave some ideas, in fact, in his tutorial. So each time I don't know what to say. Okay. Now, the second point, so the second point is to show that the spatially coupled structure, the spatially coupled code here, has a map threshold that is the same as each individual code ensemble. Okay? So when we spatially couple, we improve the belief propagation threshold, but we keep the same map threshold. That's the beauty of this spatial coupling, in fact. And how do we show this? In fact, we show much more. We show that the entropy for the uncoupled code is equal to this entropy for the spatially coupled ensemble that depends on two parameters, the chain length and the window width W. And this, in fact, is even true for all W's. And because these two functions are equal, the map threshold of the spatially coupled ensemble is equal to the original map threshold. To prove this, we use some combinatorial variant of the interpolation method. It's very similar to the old interpolation method, but it's just twisted around to prove such kind of statements where you don't want to compute the entropies, but you just want to prove that you compare system and prove that entropies are equal without computing them, okay? And this kind of method was nicely invented for constraint satisfaction problems by David Kushir and Tetali and Bayati. Okay, so we use this. These two slides are very technical, so I'm sure I don't have time, and I'll skip them. So these two slides were to show the idea of the proof. This would take 1 hour, in fact. So now I will put everything together, okay? I have a potential threshold defined for a non-coupled Ldpc ensemble, uncoupled, the one that I want to study. I do this spatial coupling construction, and I show that the belief propagation threshold of the spatial coupling construction is equal to this potential threshold. That's where spatial coupling is used as a proof technique. Okay, so here we go to the complex plane, if you wish. Okay, so now I'm in the complex plane here. I know this BP threshold, algorithmic threshold of the coupled system is smaller than the optimal map threshold of the coupled system. So that's trivial, okay? Then by one of the interpolation proofs, you show that the entropy of this coupled system is equal to the entropy of the non-coupled system, so the two thresholds are equal. So here I go back to the real plane, to the real line, okay? And by the old interpolation method that was invented for the spin glass models originally, you show that this map threshold is less than the potential threshold that was known 10 years ago, say, or maybe 8 or, okay? So what is new is this step. This is easy, and what is new is also this step. And also what is new is to put everything together and get the idea, okay? But that is the strategy. In fact, so finally you obtain that epsilon potential is equal to epsilon map because it's sandwiched here. And once you know that these two thresholds are equal, the map and BP curves, as I said, they are constrained by the area theorem, so they must be equal above the map threshold. And since the map exit curve by definition is the derivative of the entropy, you just integrate somehow your curve and you get the entropy. And this way you get the full replica symmetric formula. So, okay, if you want to do this in detail, you have some technical problems. So to do these interpolation steps, you need that the degrees of the check nodes are even. This might sound strange. I mean, I don't understand why you need this. You can generalize a bit, but you need some condition on the degrees of the check nodes. And also so where is it? To show, yeah, at some other point you also need the degrees to be large. In fact, okay, maybe not for this result, but you need when you integrate out the map curve to get back to the entropy, you have to control some regularities of the functional derivatives. So this requires large degrees. But anyway, I think I'll conclude now by saying that this is a strategy that is quite general, and we have applied it, we tried to apply it to KSAT, for example. So for KSAT, you have these phase diagrams that are much more complicated than in coding. You have many phase transitions. You have a unsat phase transition where below the unsat threshold you have solutions, and above you don't have solutions. But even in the space where you have solutions, the solutions are organized in some funny way in the Hamming space. So you have some dynamic, it's not clear in this case if it's an algorithmic threshold or what, but some kind that we call dynamic or clustering threshold where the solutions shatter in groups. And then there is a second transition that is even more funny. So, for example, suppose you want to control or compute this threshold. We are not there yet because the problem is much more complicated. But the idea would be to construct a spatially coupled KSAT formula such that this dynamic kind of threshold is boosted to one of these, okay, is boosted somewhere. So you eliminate this phase. This phase is a bit like the phase in between BP and map where your algorithms get stuck. So you would eliminate this phase in the spatially coupled formulas. And then you run your very simple favorite algorithm, like unit clause propagation, say, to find solutions below the dynamic threshold. Of course, it doesn't work up to here, because life is more complicated. But you know, if this phase disappears, it might be that your favorite analyzable algorithms, they work till here in the usual case, but suppose if this disappears, they might work better, okay? So we have done this, and in this way, we could prove better lower bounds on this SAT-unsat threshold. So for k-sat, for 3-sat, for k equals 3, clauses with 3 variables, we have the best lower bound that you find in the literature. But for k greater or equal to 4, there are non-algorithmic methods that beat our lower bound. But what is interesting is more the idea and the strategy. And you might want to analyze other phase diagrams with this strategy. Each time you have some sort of glassy phase or a phase where algorithms get stuck, maybe you can construct a bigger system where the algorithms are unstuck, okay? And this allows you not to solve the original system really, but to say something tight about these thresholds. In the case of codes, we can even compute the whole curve here. So that's a nice case, okay? So that was the general idea of this spatial coupling as a proof technique. So I'll conclude.